So to start, today it's going to be an intro to matrices, and it's going to be pretty basic. Tomorrow we'll get into a little more complicated stuff. But to start, matrix is a rectangular arrangement of numbers. So here we have a matrice, and in a matrice you can have variables, you can have negative numbers, you can have fractions, you can have decimals, you can have zeros, you can have a lot of different kind of numbers or variables inside it. And so matrices have columns and rows, and a column is like the column on a building. It's what holds it up. So yes. So in this matrice, we have two columns. Those are our columns, kind of like on a building. And then the horizontal numbers, those are our rows. Kind of like if you go to a Twins game, there's the rows.
Oh yeah, rows is the symbol for Aphrodite.
Okay, so columns and rows are important because that is how we name a matrix. So to name a matrix, you name it first by its row and then its column. So in this example here, this is a 2 by 3 matrix because it has 2 rows and 3 columns. And that's how we name a matrix. It's by its rows and columns. Also, when we name a matrix, we use capital letters. So like for this matrix, I could name it like S, the matrix X, or M. We use capital letters when naming them. So, based on rows and columns, what would this be? A what by what?
4 by 3. 3 by 4.
It's rows then columns. So 1, 2, 3, 4. 4 by 3. First the rows, then the columns. What about this one? Number 2. 4
by 2.
Yes, that's important. It's not a. It's a 4 by 2.
2 4.
Not a 4-2.
Not a 4 2.
2 4.
By 4.
This 3. What's 3?
2 by 4. 3 by 2.
No. Yes.
And then this last one,
3 by 1.
By 2.
a 3 by 2. Another important thing is, so let's go back to this page, the first page here. In this matrix, each variable or number has like a number or a name attached with it. So this would be row 1, column 1, because it's the first row in the first column. This one would be row 2, column 1. This would be row 1, column 2. And row 2, column 2. So this, it seems kind of pointless right now, but we will use it tomorrow when we're multiplying matrices, and it gets kind of complicated. So if you can look and say, oh, this is in the first row, second column, that will help you.
So is it for like data?
It's for data, yeah. We're going to talk about some of the applications of it, but yeah, you're exactly right. So on your iPad, I want you to name every spot in a 3 by 3 matrice, like I did here. Yep. This, you can just go to like this first page. So I'll start you off and then you can finish. What would this be? Row 1, column 1. What about this one?
Row 1, column 2.
So on your iPad, fill the rest in. This is important to know how to do.
So how like negative at 2?
Shh. Are you doing this?
Then it will help.
Okay.
I did it.
Sorry.
You messed up my seat.
Okay, so let's fill this in together. This is row
2. 3.
row 2, column 2. Row 3, column 2. Row 3, column 3. So if you can do that, then you'll be set for tomorrow. What? Yes, but the more you talk, the longer it will take to get there. Okay, so we did that. Lastly, if the matrix has the same number of rows and columns, we call that a square matrix. Yes? So what kind of square matrix is this? Yep. A 3 by 3. Okay. So now, I want to multiply this matrix by 2. So I'm going to say 2 times this matrix. Can someone raise their hand and tell me what they think happens? How would I solve this problem?
Multiply 2 by every.
No.
Take a guess. You raise your hand.
There'd be 2 of those.
6 by 6.
There'd be 2 right by each other.
Okay. Any other ideas?
Adding to each other.
Well, actually, all the side chatter needs to stop. You take every point within the matrice and multiply it by 2. So our final matrice would look like this. Negative 24, 2. What would this one be? Row 1, column 3.
Negative 16 is I don't like that. 16, 26, 36, negative 2, negative 28, negative 8.
So this is called, when you're taking a number and multiplying it by a matrix, this is called scalar multiplication. So whatever this number is, you take it, multiply it by everything inside of the matrix. Okay. So let's name these. Some more practice. What is this? And it's also called a what? Where? What about this one? What about this one? 1 by 3. Someone last hour asked me if you could have a 1 by 1. So that would look like this, right? Is that possible?
That's
Yeah.
absolute value. Yeah. No, it's not.
Nope, this is still a matrix because we have our brackets. Absolute value would be like this.
That's great.
Okay. So these matrices are rectangular representations of data. We use them like in the seating chart. So right now you're in like kind of like a matrice because there's a spot and it's a bunch of little spots. Your monthly schedule, a school's daily schedule, or a photo album, all of these things have a rectangular arrangement, and that's what a matrix is. So let's talk about a use for a matrix. And this is something you'll see on your homework, so I would pay attention. So you can use matrices to plot points or a figure. So here we have a quadrilateral. And my question for you is, on your iPad you can see better, but what is this point? 1, 2. So that point is point 1, 2. So take that point, and where do you see it on this in this matrix of numbers?
Column 1, row 1, and column 1, row 2.
Yep. So we see it right here. Shh. All that needs to stop. So based on that, what row do you think is our x, and what row do you think is our y value?
Row 1.
Judging from the thing that you know, I think
X and y.
Wait, what if you have 3?
Good question. Last hour I asked that. So a third one, that would be like our z coordinate, and that means you would be talking like in 3D. So that's possible. Then someone asked me about like a fourth variable.
you do like 90.
40.
No. The most you could do is 3 for if you're going to plot points. But you won't have any 3D ones because to plot those points would be super, super hard. I had to do it in college and it's pretty tricky. So that is how we use matrices to plot points, like we did here with the quadrilateral. What else? So that's it for this one. So this first row is x, second row is y. So -2, 1, that's like this point. -2, 1, up 1. -3, down 1.
What's the difference from that and the table?
There isn't a difference. This is just, we can use matrices to like solve equations and stuff. So this is just a different way of representing data.
You can't use a table to solve the equation, just a matrix.
Well, today we're talking about matrices. So this slide is about like how we use matrices, and this is one way we can use them. So if we have a 2 by whatever matrix, we can make a figure out of it and then plot it. And now we'll move on and see another part application of it. It's really hard. It's the alignment's kind of off, but the Z kind of goes like that, and it's complicated to plot. It's
You have to like make it so it's like layered, so like it looks like it's 3D.
yeah, it's way beyond this. So let's look at an example. So these are our points for a triangle, and I have already done this. So -3, 2. So that's our original triangle based on this matrix, right? -3, 2, 1, 3, 2, -2. Our points are those are our 3 points that make up that triangle. Did I? Oh, 2, yep, thank you for that. So now part A asks us to do a translation left 3 units. So do you remember when we graphed like logs? And when we said left, what did that really mean? So now we have to reverse our thinking again. And whenever it says left or right, you're going to do it exactly as it says. So when it says left 3 units, you're actually going to move it 3 units to the left. So if we move our points 3 units to the left, are we moving our x points or our y points? X. So this row is going to change. And if we're going 3 to the left, we're minusing 3. I'd write this down because this will help you with your homework. So now, is it telling us anything with our y points? Does this problem tell us anything? So, does it? What does it tell us? Okay. So there's nothing for y, so we just can put zeros because we're not going to change them. All we're going to do is slide it over 3 to the left. So to solve this addition, you take that point and add it to that point. That one to that one. And our matrix will come out to be -6, -2, -1, 2, 3, and -2. Our y stayed the same and our x has moved 3 to the left. So that would look like this. So -6, 1, 2, 3, 4, 5, 6, right there, and then up 2. So we just translated that. Now, what kind of transformation is happening here? What's happening to our x's? Going left 4. If that was a positive 4, where would it be going?
Right.
Right 4.
So not good. Can I go to the bathroom?
Yes. What is happening to the y values? Going down 3. And if it was positive, it would be going up 3. So on your iPad, do this addition. Practice doing this addition. So you're taking row 1, column 1, and adding it to the other row 1, column 1. Who got this?
Negative 5, I think.
What?
Is that negative 5? Yeah. Negative 2 minus 8.
Which one?
Negative 2.
Oh, yep, negative 5. Good job. Nice catch. Okay, so when we add or subtract, shh. Oh, that side chatter, please stop. So when you add or subtract, you're taking each position and adding or subtracting it to the same spot on the other matrix C. Here again, we have scalar multiplication. When we do scalar, we take that 2 and multiply it by what? Everything inside. So each of these points times 2. So in the end, we would still get a 2 by 3 matrix. Doesn't get bigger or smaller. For what one? Oh, the transformation would be, so if you're timesing that matrix by 2, what do you think happens to it? It gets bigger. Yep. So write that it gets 2 times bigger. Okay. So now let's talk about reflections. I want everyone to pay extra close attention because this can be pretty confusing. So here's our matrix. And those points are plotted right here. If we reflect a point over the x-axis, first, which is our x-axis? Is it this one or this one? 1 or 2? So here's our x-axis. And we want to reflect the figure over that x-axis. So let's first look at B. If we reflect that over x, what would our new point be? So we move this over the x, so it'd be what? 2, negative 6. So our point went from 2, 6 to 2, negative 6. Did our x change or our y change? Y. It was multiplied by negative 1. So if you're reflecting over the x-axis, you multiply your y points by negative 1. So for this one, that would look like I could just go right through and multiply my y points by negative 1. So my x's, those will stay the same. We can just write those down. Those will stay negative 5, 2, negative 4. But now these are all multiplied by negative. So negative 3, negative 6, negative 2. So this would be the matrix for a reflection over the x. Now let's look at what happens when we reflect that point over the y. So our y-axis runs up and down, so that's this right here. And if we look at B again, and we reflect it over, what would our new point be? Negative 2, 6. So now our x value changed. So these values changed. So a reflection over the y-axis, you're taking each of your x points and multiplying it by negative 1. So that matrix would look like 5, negative 2, 4, 3, 6, negative 2. So reverse thinking, reflecting over the x, multiplying by negative 1. Reflecting over the y, multiplying our x's by negative 1. And the last reflection we're going to talk about is a reflection over the line y equals x. Can anyone take a guess at what they think happens? Shh. Someone raise their hand and tell me what they think happens. So here, let me first draw my line. The first thing I want to do, I'm going to move this figure to the reflection. Tell me where it would go, where it looks about right.
Right.
No.
Does that look right?
No left. Left will work.
Yeah, that's it.
There. So that would be a reflection over the line y equals x. So let's look at the points. This point is now, so that B point, B prime, is now 6, 2. What do you notice when comparing those numbers? They flip. So a reflection over the line y equals x is you flip them. So that matrix, if we took our original matrix, and let's say we didn't even want to draw it, like we just wanted to look at our matrix and say, oh, what would it look like reflecting it over the line y equals x? We could just take this and flip our points. So I'd flip these, right? 3, negative 5, 6, 2, negative 2, 4. So you're flipping your x and y's when it's over.
Multiply each one by negative.
Well, when did we what? So if we're reflecting over the x, then we multiplied each of our y points by negative 1.
Okay.
You might want to write that down, because you might forget it.
Wrote it down.
And if we're reflecting over the y-axis, if we're reflecting over the y-axis, we multiply each of our x points by negative 1. And then over y equals x, we flip our x's and y's. This will be on your homework, so it's worth writing down and understanding. Everyone got that? Any questions? Give me a fist of 5 if you understand that. Yes. What? No. No. Yes. Okay. That's all we're doing for the day. But one thing I want to talk about is when you're adding and subtracting matrices, there's something that's really important. So let's say I have a matrix that's 1, 2, 1, 2, 2, 2, and I want to add it to 2, 2, 1, 1. So this, what size is this matrix? It's a what by what? And what's this one? Raise your hand if you think we can add those two together.
Yeah.
Raise your hand if you think you can't add them together. Annika, do you think you know why? Yes, she's exactly right. So if you're asked to add two matrices that are different dimensions, you can't do it. It's not possible because what you run into is here we have row 3, column 1. Well, we come over here because we want to add it to row 3, column 1. There's no row 3, column 1. So if you have this different size matrices, it's no solution or not possible. Can't do it. They have to be the same size. Any questions on that? And this is also important because tomorrow when we multiply matrices, we actually can multiply matrices of different size. Yes?
You add them the same size and column, or and rows, just not columns.
Has to be the same number of rows and same number of columns. Good question. So your homework tonight is on Schoology. It should be under day 1 of matrices or something like that. And that will be due tomorrow. You have plenty of time, so get started. You might be able to finish.